Alright, here it is, 3:40 on a Friday afternoon, and I'm not procrastinating. Since I'm going to be away, I'm just going to do these lessons now, and I'm on a tablet with a pen, and it's a little out of practice with that, so it might not be too smooth. Okay, is the statement sine alpha plus beta the sine of alpha plus beta, is that the same as sine alpha plus sine beta? Say, don't know. So let's check. Thinner line, hang on, thin line. Verify your answers with alpha is pi over 3 and beta is pi over 6. So we're doing a verification. It's a left side. So the left side is the sine. So alpha is pi over 3 and beta or beta. Okay, so that's, we need 6. This is 2/6 plus 1/6 is 3/6, which is pi over 2. And the sine of pi over 2 is 1. So the right side is the sine of pi over 3 plus the sine of pi over 6. So the sine of pi over 3 is 1/2. Is that true? No, it's root 3 over 2. And the sine of pi over 6 is 1/2. So that has a common denominator, and we get root 3 plus 1 over 2, which is not 1, right? So we'd say, no, not true. So we know that the sine of alpha, and really all it takes is one counterexample, right? We don't have to do a bunch of these. If it's not true for one, it's just not true. Right? It's not an identity. Remember, identities must be true for all values. So is it equal? No, it is not equal. All right. So if the above statement is not true, then what is the sine of alpha plus beta? Well, we got a formula sheet. And on the formula sheet, we have the sum identities, right, when you're adding sum, and the difference identities when you're subtracting difference. So verify that sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta is true. Verify that it's true using alpha is pi over 3 and beta is pi over 6. Okay, so the left side, well, we already worked that out, right? That's up above. So left side, let's just say from above is equal to 1. Okay, what's the right side? So it's sine alpha, so sine pi over 3, cos beta, cos pi over 6. Now let's throw some nice little brackets around there. Plus cos alpha, so cos pi over 3, times the sine of beta, which is pi over 6. So sine pi over 3, that's root 3 over 2. Let's enclose that in brackets. The cos of pi over 6 is also root 3 over 2. The cos of pi over 3 is 1/2. And the sine of pi over 6 is 1/2. So root 3 times root 3 is 3, so we get 3/4. Half times a half is 1/4, and 3/4 plus 1/4 is 1. And we put a big hooray, and we say, yes, true, exclamation, exclamation. And huzzahs. All right. The hidden reveal is that there was nothing there. That's kind of funny. Verify two of these identities numerically with alpha is pi over 3 and beta is pi over 6. Verify two of these identities. How about verify these two identities numerically? That would seem to make sense to me. All right, so same deal. We've got the left-hand side. So when you're verifying identities, remember, you keep stuff separate. There's no crossover here. I can't say, oh, let's divide both sides by, no, okay? You just work separately. So the left side is the cos of pi over 3 plus pi over 6. Okay, so remember, that's 2/6 plus 1/6 is the cos of 3 pi over 6, which is the cosine of pi over 2, which is, pause for effect, 0. You might notice this goes a little faster than in the class because you can pause and I don't have to. So the right side is cos alpha. I do have to get my pen positioned on the tablet. So the cos of alpha, cos pi over 3, cos beta, cos pi over 6, minus, okay, it's interesting, you don't have to memorize these, they're on the formula sheet, minus sine alpha, so the sine of pi over 3, sine beta, sine pi over 6. I gotta do little tablet tricks here. Equals, okay, so the cosine of pi over 3 is 1/2. We'll just throw these in parentheses, right, because we're multiplying. Cosine of pi over 6 is root 3 over 2 minus the sine of pi over 3, which is root 3 over 2, and the sine of pi over 6, which is 1/2. So we have root 3 over 4 minus root 3 over 4, which is equal to 0. The left side is equal to the right side. So we have verified. Now remember, we've verified. We haven't proven this is true. We've simply verified that for these two values, for alpha is pi over 3 and beta is pi over 6, we've verified that this is in fact true. Okay, let's try this guy. So the tan, this is the tan of a difference, right? It's a difference identity. So let's just run a little line down here. The left side is equal to the tan of pi over 3 minus pi over 6. So this is 2/6 minus 1/6, so it's the tan of pi over 6. And the tangent of pi over 6, so pi over 6, so tan is sine over cos, so it's going to be 1 over root 3, right? And if you think 1 over root 3, just write root 3 over 3. And then separately, we're going to do the right side. So the right side is equal to the tangent of alpha, tan of pi over 3, minus the tangent of beta, so minus tan pi over 6, over 1 plus tan pi over 3 times, times the tangent of, let's bracket this, tan pi over 3 times the tan of pi over 6. So that's equal to, okay, so the tan of pi over 3, so that's just root 3. The tan of pi over 6, we already did that, that's root 3 over 3. Oh, it's getting fractiony. So I'm going to write that root 3 as a root 3 over 1. Because I'm going to actually work this out, right? Over 1 plus, okay, tan of pi over 3. At least we've already done these, right? So this is root 3, or root 3 over 1, times the tan of pi over 6, which is root 3 over 3. And so I'm just going to go sideways here so that I've got more room here. Common denominator up top is 3. So this needs a 3. So this is going to be, the numerator will be 3 root 3 minus root 3. So you see this is root 3 over 3. That's what we've got here. This is root 3 over 1. So we write it as 3 root 3 over 3 multiplied by 3 top and bottom over 1 plus, okay, so root 3 times root 3 is 3, and 1 times 3 is 3. So this is just 1 plus 3 over 3. Let's write that, 3 over 3. Moving down, extending our little line. So we've got here 2 root 3. Let's put an equal sign here, right? It's still carrying. 2 root 3 over 3 over 2. All right. Okay, sure. So we'll write that as 2 over 1. Let's make it a complex fraction too. So we get 2 root 3 over 3 times, and we're going to flip this guy, right? 1 half. Okay, 2 cancels. And we're left with root 3 over 3. At which point we say, well, what is it we were doing? Oh, yeah, I wanted to see, oh look, root 3 over 3. So we now can say left side equals right side. And have we proved it? No, but we verified it for those two values. Okay, one page down. Use the sum identities to show that the sine of 2 alpha, the sine of 2 alpha is 2 times sine alpha cos alpha. Okay, so in essence, we're kind of proving these identities, right? If I'm showing this, then I'm proving it. So the left side, now we're using the sum identity. So the left side is the sine of 2 alpha. So the sum identity, well, let's turn this into a sum. It's the sine of alpha plus alpha. Alpha plus alpha is 2 alpha. But the definition for the sine of alpha plus alpha, well, that identity is sine A. Now, we should have this identity somewhere. Let's just go back and take a look. You remember, you'll have this on your formula sheet. So it's sine alpha plus beta, right? So it's sine alpha cos beta. So it's the sine of the first plus times the cos of the second. Now, in our case, though, they're both alphas. So all we're doing is filling in, and we can look at the sum identity while we're doing this. Just say, so it's sine alpha cos alpha plus cos alpha sine alpha. Well, in a sense, it doesn't matter what order you multiply things in. So here I can just write this. So it's sine alpha cos alpha plus, and let's just rewrite this as sine alpha cos alpha. And how many of these sine alpha cos alphas do we have? We have 2 of them. So that's 2 sine alpha cos alpha, which is the right-hand side. So we have used the sum identity to prove this double angle identity. Okay, here's another double angle identity. This says the cos of 2 times an angle is cos squared alpha minus sine squared alpha. All right, so same idea, right? Left side is cos of 2 alpha. We're going to use the sum identity, so we write the cos of alpha plus alpha. We look back, where it's like 2 pages up. I'm not going back there, but if you look over to your left, you will see that the cos of alpha plus beta is cos. So in this case, they're both the same, right? So it's going to be cos alpha cos alpha minus, there's that thing with the cos one, sine alpha sine alpha, right? This is your beta, but it's an alpha, so where we would normally see a beta, we're writing the alpha, And that's equal to cos squared alpha minus sine squared alpha, which is equal to the right-hand side. So that's a proof using the sum or the sum identities, I guess. It's a proof using the sum identity of this, which is a double angle identity, right? Double the angle. And now the tangent. Okay, so the left side, that's the tan of 2 alpha. So I'm writing this out again, right? I want to do this because I want a starting point that has to be something that I can see. All right, so how do we prove the sum identities? We change 2 alpha into alpha plus alpha. We then go through the sum identity for tan of alpha plus beta, but everywhere we see an alpha, we write alpha. Everywhere we see a beta, we write alpha. So it's tan alpha plus tan alpha over 1 minus tan alpha times tan alpha. So this is tan alpha plus, so there's 2 of these tan alphas. And this is 1 minus tan squared alpha, which equals the right-hand side. When I do this, I should get all different like sound effects and stuff. Number 4. Use the identity cos 2 alpha is equal to cos squared alpha minus sine squared alpha to determine an identity for cos 2 alpha in terms of cos alpha first, and then in terms of sine alpha. Okay, so we're given cos 2 alpha is cos squared minus sine squared, and what I want to have is just cosine. So here's what we're going to do. We will start with cos 2 alpha is equal to cos squared alpha minus sine squared alpha. I'm not proving an identity, I'm just kind of actually reforming this. So I just want cosine. It means I got to get rid of the sine. Well, wait, it's not sine, it's sine squared. So again, anytime you see a squared, you look for your Pythagorean identities. And so sine squared is really 1 minus cos squared. I see now everything's in terms of cosine. So expanding away a set of brackets, we got cos squared alpha minus 1 plus cos squared alpha, which is 2 cos squared alpha minus 1. So, and that's the cos of 2 alpha. So there's another identity, right? It's a form of a double angle identity for cosine. Okay, what if I want to do this in terms of sine alpha? Well, let's get rid of cos squared. So cos of 2 alpha is equal to, let's just start with the statement, right? We need a starting point, which is the actual identity. Instead of cos squared, we're going to go 1 minus sine squared, right? And that comes from the identity cos squared, or sine squared theta plus cos squared theta is equal to 1. Okay, in this case alpha, minus sine squared alpha, nice alpha. It's an infinite alpha. Wait, I can just control Z that away. Sine squared alpha. So I got 1 minus sine squared minus a 1 minus 2 sine squared alpha. And what's that? That's the cosine of 2 alpha. So in terms of cos 2 alpha is 2 cos squared alpha minus 1. In terms of sine, cos 2 alpha is 1 minus 2 sine squared alpha. And lo and behold, or go down a page, and behold, as seen on the formula sheet, so the sine of 2 alpha, it's just one little lonely 2 sine alpha cos alpha. But the double angle identity for cosine can be cos squared alpha minus sine squared alpha, or, replacing this, 2 cos squared alpha minus 1, or replacing this, 1 minus 2 sine squared alpha. And tan 2 alpha is just this guy, 2 tan alpha over 1 minus tan squared alpha. What use is any of this anyways? Well, here's a use. Write each expression as a single trig function. So what I'm looking for is somewhere on the formula sheet, do I see something that looks like cos alpha, cos beta, right? The cos of an angle times the cos of a different angle plus the sine of that same angle times the sine of that same angle. And if we look on the formula sheet, we will see that we have cos alpha, cos beta minus sine alpha, sine beta. Oops, that's the sum identity, but we need a plus here. So we look at the difference identity and we see we got cos alpha, cos beta plus sine alpha, sine beta. And so that's the difference identity. That's the cos. So that's the cos of alpha minus beta, which means this equation here can be expressed as, that's this side, it can be expressed as the cos. I guess I should write an equal sign if I'm going to express it. Well, I can, it could be, well, no, I don't want that. Let's get rid of that too. Go away. So this, okay, ignore this. I am going down, is equal to the cos of alpha, 15 degrees, remember degrees, if it's degrees, you got to have degrees, minus beta, which is the cosine of negative 25 degrees, which, if we remember our where we are, cos of negative 25 degrees is the same as cos of 25 degrees, right? Negative 25 degrees, that's the reference angle, and that's the rotation angle, reference angle for both of these is 25 degrees, and cosine is positive down here. So, you know, on the unit ugly oval, these have the same x value, right? The same cos value. Same cos value. Okay, I have 2 tan 20 degrees over 1 minus tan squared 20 degrees, right? I have something that looks a lot like that. Well, okay, it looks exactly like that, which means I have found an identity. So this is equal to, this is putting in a slash, this is equal to what? It's equal to this. The tan of 2 times 20 degrees, right? That's in degrees, which is equal to the tan of 40 degrees, right? So this is equal to tan 40 degrees. All right, let's go to the big reveal here. And somebody had fun sticking those things in there. All right, oh, thank God they're there at the top. I can see them all now. Simplify and then state the exact value for. So here's the deal, right? You're looking at your formula sheet. You see cos squared angle minus sine squared, same angle. You go up here and you say that's this guy here, which means that this is equal to the cos of 2 times 15 degrees, which is the cos of 30 degrees. Okay, so simplify, okay, and then state the exact value. So if you see the word state exact value, you know you're dealing with one of the exact values. And the cosine of 30 degrees is root 3 over 2. Okay, I got sine cos plus cos sine. Sine cos plus, so here we go. That's alpha, that's beta, alpha, beta, right, alpha. And that's equal to the sine of pi over 8 plus 9 pi over 8. So I got 1 plus 9, excuse me, which is 10 pi over 8. Which is, excuse me, again, the sine of 5 pi over 4, right? Sine 5 pi over 4, let's see, that's a quadrant 3 angle. There's 5 pi over 4, right? Because this is pi, which is 4 pi over 4. So it has the same value as a reference angle pi over 4, but with a negative, so it's negative root 2 over 2. Okay, you're just supposed to know that anyways, right? Okay, no hidden thing to unhide here. Ah, and here they are again. And again, right, you're always wanting to do this with your formula sheet handy. We gave it to you. It's big, it's bright, it's orange. So the sine of 105 degrees. All right, can I express that as 2 times? No, that would be silly. So can I express that as 2 angles? Okay, sure, I can do it as 104 degrees plus 1 degree, but it wants the exact value. So I need magic numbers, right? What are our magic numbers? 30 degrees, 45 degrees, 60 degrees, any multiple of these guys, right? So I could take 60 plus 45, right? That would work. 105 degrees is, so that's going to be the same as the sine of 60 degrees plus 45 degrees. But wait, that's this, right? So then I write sine 60 degrees cos beta, this is my beta now, 45 degrees plus cos alpha, cos 60 degrees, sine 45 degrees. Let's clean, make explicit this. There we go. All right, so sine 60 is root 3 over 2. Cos of 45 is root 2 over 2. Sine 105 is going to be positive, right? So hopefully we are positive here. The cos of 60 degrees is 1/2. Let's do this with this. And the sine of 45 degrees is root 2 over 2. All right, so what do we get? We have root 6 over 4 plus root 2 over 4, which is root 6 plus root 2, and we've got the common denominator, over 4. So there's our answer. Okay. Now, if you wanted to check this, you could do sine 105, make sure your calculator's in degree mode, and you could do this, root 6 plus root 2 over 4, and you will get the same number. The tan of pi over 12. Okay, so either I need two numbers that add to pi over 12. Now, what is pi over 12, right? That's pretty small, so they're probably not going to add. So I'm looking for a difference here. I'm looking for a difference of pi over 12. 1 pi over 12. So what if I did, I want 1 pi over 12. So what if I did 4 pi over 12? Now that's pi over 3, right? That's good. Pi over 3 is an exact value. We know what to do with that. And 4 pi over 12 minus 3 pi over 12, right? This is 1/12. 4/12 minus 3/12, right, is 1/12. 3 pi over 12 is the tan of pi over 4. Okay, so these are our numbers, right? I mean, what were our numbers again? 30 degrees, 45 degrees, 60 degrees. That's pi over 6, pi over 4, pi over 3. Okay, so when I want to make twelfths, I want to get 1/12. I could do like two of these, 2 pi over minus 1/12. I can't really get a 12th out of here. So in this case, we come over here and say I can get 3/12, and I can get 2/12. Or sorry, what do I mean? 4/12, right? Get that to be multiply that by 4, multiply this by 3, so you got 4/12 and 3/12. Those can be combined to give you 1/12. All right, so what is this? It's the tan of, okay, 4/12. It's the tan of pi over 3 minus, and 3/12 pi over 4. Okay, now we use the formula for the difference of tans, right? So it's the tan of the first, pi over 3, minus the tangent of the second, pi over 4, all over 1 plus the product of these two, tan pi over 3 times tan pi over 4. Okay, again, we're using a difference identity here. This is the difference identity, right? 4/12, 3/12. Remember the 4/12. 4/12 is actually pi over 3, and it's equivalent, right? So you look at these guys, just make them equivalents, right? So if you're dealing with 12s, just say I got 2 pi over 12, I've got 3 pi over 12, and I've got 4 pi over 12. Okay, which of these? We could have actually done this minus this too, right? That would have worked. So we could have done tan of pi over 4 minus pi over 6. So you have choices, right? Because pi over 12 really is 15 degrees, right? So you could do 60 minus 45 or 45 minus 30 if you're into degrees, which I'm not at all into degrees. All right, so the tan of pi over 3. Tan of pi over 3 is root 3 minus tan of pi over 4 is 1 over, I think it's going to be a little bit worse down here, 1 plus. Oh, well, we just did these guys, right? So we've got 1 plus root 3 times 1. Okay, so let's simplify. What do we got? Root 3 minus 1 over 1 plus root 3. And you say, I'm done. No, you're not. You have to rationalize the denominator. So we multiply by the conjugate, right? Same two terms, 1 and the root 3, but it's 1 minus root 3. And it's not just, it's the conjugate over the conjugate, right? It's 1 minus root 3 over 1 minus, that's a minus root 3. I barely see that. Let's do this. 1 minus root 3. Okay, so the bottom becomes 1. It's a difference of squares, right? It's 1 minus 3. Okay, so the bottom, aka the denominator. And up here we've got root 3 minus 3. All right, let's write this down as we go. So we'll FOIL it out. Root 3 minus 3 minus 1 minus root 3. Okay, so let's, I ran up, oh God. First I run off the tablet. Okay, so root 3 minus root 3 is, wait a second here. Root 3 minus 1, 1 minus root 3, root 3 minus 3 minus 1 plus, that's a plus, plus root 3. Okay, root 3 plus 3. So we've got 2 root 3 minus 4 over negative 2. Let's put an equal sign here because it's still equal to that. Okay, I can divide by negative 2. So this divided by negative 2. Well, first off, let's do this. Okay. This divided by negative 2 is going to be positive 2. This divided by negative 2 will be minus root 3. So we end up with 2 minus root 3. One more time. Okay, let's just divide this. Divide this by negative. We get negative root 3. Divide this, right? That's plus 2, which we will then write as 2 minus root 3. Okay, one more time. Factor a 2 out of the top. Gives me root 3 minus 2. Got a 2 on the bottom, negative 2. These guys cancel. Leaving me with negative 1. Change these signs. There you go. 2 minus root 3. Done. Okay, if you had time, wanted to verify again, you could do this by taking the tan of pi over 12 and then taking, well, let's do it. Let me, hang on, I'm going to pause, I'm going to open up a calculator. I'm back. Okay, it was just cleared, so the tan of pi divided by 12 and then 2 minus root 3. Drum roll. They're the same. Okay, that's good. So that's true. And this is exact. Don't give me the decimals. I do not want these ever. Never. Look, see the sign, the slash right there. See, it's through the number. Don't do that ever. Okay, and again, for number 8, we are 8, 7, 9, so, but 8 has 3. Okay, just keep going. If the cos of, it's been 36 minutes. If the cos of if cos theta is negative 3/4 and sine beta is negative 1/3, where theta is between pi and 3 pi over 2, also known as quadrant 3. So theta is a quadrant 3 angle, and beta is between 3 pi over 2, aka quadrant 4. That's really ugly. Then determine the exact value of each of the following. Okay, cos 2 theta. Okay, all right, well, so we don't have to worry about, okay, we're just going to worry about cos 2 theta, cos of 2 times an angle. So we can go cos squared. So if we know the cosine, then let's not bring in this sine, right? There's no point in doing that. I have to figure out the sine, and I've got x and I've got r, and I could figure out y, but I don't need to. Why? Why figure out y? No, figure out y. Okay, so let's just go with 2 cos squared theta minus 1. This identity only involves cosine. Okay, so that's 2. What's cos squared theta? Well, cos theta is negative 3/4. So cos squared theta is negative 3/4 quantity squared minus 1, which is 2 times 9/16 minus 1. Okay, let's just go over here. So 2 times 9/16 is 9/8 minus 1. And 1 is 8/8. So 9/8 minus 8/8 is 1/8. 1/8. Okay, can't check that on my calculator because, well, I could do an inverse cos on this and get an angle and then mess stuff up horribly, so I'm not going to do that. The cotan of 2 beta. Okay, so the cotan. Well, the cotan is 1 over tangent. So it's 1 over the tan of 2 beta. All right, well, we know what tan of 2 beta is, right? We have a formula. It's up here. The double angle, right? This time we're using beta, so it's going to be 2 tan beta. Okay, so that's equal to 1 over, okay, and now we put the thing in, so it's 2 tan beta over 1 minus tan squared beta. So we have 1 over, so we're just going to flip this over, right? So it's just 1 minus tan squared. We're going to take 1 and multiply it by the reciprocal. 1 over tan squared beta over 2 tan beta. Okay, at this point, we have to say beta. What's beta? Well, what's the tan of beta? Well, we've got the sine of beta, right? We know that the sine of beta is negative 1/3, and we know that beta is a quadrant 4 angle, right? If I just tell you the sine of beta is negative 1/3, you only know that it's in quadrant 2 or quadrant 4. This nails it down. It's a quadrant 4 angle. Sine is y over r. But wait a sec, it's y is negative 1. Okay, so let's go down here. We'll go over here. Let's separate this out. Wow, that was not a nice circle. That's not either, but at least I'm into this quadrant now. So we know that r is 3. Okay, what do we know here? We know sine of beta is negative 1/3. It's a quadrant 4. We know that y is negative 1. We know that r is 3. We get x is the square root of r squared minus y squared, which is the square root of 9 minus 1, which is root 8, which is 2 root 2. That immediately jumps into your head, 2 root 2. And, okay, what do we need? Well, we need the tan of beta, right? Well, what's tangent? So tangent in quadrant 4 will also be negative, right? Tan is negative in 2 and 4. And tangent is defined as y over x. Y over x. All right, so let's do it. We'll move over here. Is equal to 1 minus negative 1 over 2 root 2. At this point, erase. Oh, look at that. That worked. Negative 1. All right, hang on. 1 minus. Minus doesn't look right. 1 minus. Okay, let's call it negative 1 over root 8, right? Because we're going to be squaring it. Negative 1 over root 8 squared, right? And on the bottom, we've got 2 times, okay, negative 1 over. Now let's call it 2 root 2, because these 2's are going to cancel. Okay, so we've got 1 minus 1/8. 1 minus 1/8 over, cancel, cancel. This is negative 1 over root 2, negative 1 over root 2. Don't panic yet. We're going to flip this, right? So this is going to be 7/8 times, we're going to flip that, negative root 2 over 1, giving us negative 7 root 2 over 8. There we indicate our triumphant value. Look, I've done it. Sine alpha plus beta. Okay. So what do we know? Oh, sorry. Sine theta plus beta. So we know cos theta. Okay, wait a sec. What are we doing again? Okay, we've got the sine of theta plus beta. So there's no choice, right? We have to use this formula. So let's just fill in the formula that we're going to use. Equals sine theta cos beta, or beta, cos plus cos theta, which is actually theta. It's cos theta sine beta. Okay, so we know that sine theta, sine of theta, we know the sine of theta as given to us. Okay, we don't know the sine of theta. So we're going to have to work these out, right? So what do we know? What do we know? We know the cos of theta, okay? So we know this. And we know the sine of beta, okay? So I'm pointing to it with my finger. So we know this. Clean this up so we can actually see this. Okay, so we know this. But we need, in the formula, we're going to need the sine of theta, right? And the cosine of beta. Okay, so what's the sine of theta? Okay, here, need scratchy paper here. So cos theta is negative 3/4. Theta is in quadrant 3. So in quadrant 3, and cos theta is -3, so the x value is -3, the r value is 4. This will be the square root of, and here's where it's going to get tricky, right? I'm just going to square this. This is 16 minus 9. This is root 7, but it's going down, so it's -√7. So sine theta is -√7 over 4. Okay, and we already did some junk with beta, so we know that cos of beta, which is a quadrant 4 angle, so this is positive. So cos beta is 2√2, right, x over r, 2√2 over 3. So the cos of beta, okay, maybe we should write this down here where we can see stuff. Okay, so sine theta is -√7 over 4. Cos theta is -3/4, right? That was given to us up here somewhere. Sine beta, which was given to us, is -1/3. And cos beta is x over r, which is 2√2 over 3. Okay, so it's all consolidated now. You're going to see questions like this. I was going to tell you, you're going to see questions like this, right? So, and remember, it just goes back to the first days, right? If I give you the sine of theta, you can figure out everything else. You have y and r, you get x, you figure out cosine, you figure out tan, you figure out cotan, you figure out secant, you figure out cosecant. You just have to know which quadrant this is in. Anyways, now we can fill in numbers. Sine theta is -√7 over 4. Cos beta is 2√2 over 3. 2√2 over 3 plus cos theta is -3/4. It's actually a nice number. Sine beta is negative. That's also a nice number. -1/3, right? Ooh, these guys are going to cancel down. Dang, you can barely see the negative there. That's okay. What was this? -3/4, -1/3. Okay, I'm going to extend the page. Drag it up a bit. All right, what do we got here? We've got -2√14 over 12 plus, okay, 3's cancel. And when I cancel, I mean they're 1. Negative times negative, so we get 1/4. So it's +1/4. All right, two choices. I could turn this to sixths, and then I have to turn everything to twelfths, so let's not do that. Let's just turn this to twelfths, right? So this is 3/12. See, so here's the thing. It's chess. It's looking ahead, right? If I take this down to -√14 over 6, then when I look for the common denominator 6 and 4, it turns into 12. So let's write 12. Let's put the positive first. Let's be positive, 3, and this is 2√14. So we have 3 minus 2√14 over 12, or -2√14 plus 3 over 12. That could be a variation of that, but that's the answer. And if you happen to be watching this and you've stuck around this long, good for you. I mean, I stuck around this long. It's like 4:30 on a Friday afternoon. Okay, what's going on here? The tan of angle B is 3 over √5, and the cosine of angle, so the tan is positive, right? So you start thinking it's Q1 and Q3. The cosine is less than 0, which is Q2 and Q3. So we are looking at a quadrant 3 angle, right? And what does that mean? Well, this is, what's tangent? It's y over x, right? So y, this is -3, and this is negative, right? So let's go down here. Y is equal to -3. X is equal to -√5. R is equal to the square root of x squared plus y squared, -√5 quantity squared, plus -3 quantity squared. That's 25 plus 9. No, it's not 25. That's root 5 squared. So it's 5 plus 9. So root 14. Okay, there we go. We got x, we got y, we got r. It gives us everything except the exact value of the sine of 2b or not 2b. But the question is the sine of 2b. Okay, got a formula for that? Sine of 2b is 2 sine b cos b. Right? This is the one. It's all by so this too, right? It's cosine that gets fancy, right? The double angle for cos. It's like you can do it all as cos, you can do it all as sine, or you can do it as one of each. But not this. This is just 2 sine b cos b, right? So you see sine 2b here. So that's your b here. So that is the b, and that's the b. 2 sine b. Okay, sine is y over r. That's negative 3 over root 14. Cos b, that's x. That's negative root 5 over root 14. This is not such a bad, let's call this 2 over 1. It's not such a bad thing, right? Because it's going to self-rationalize. Well, it's just going to work out to be rational. All right, so we've got negative 6, positive, so we got 6 root 5 over 14, which some of you will leave like that because I didn't want that half mark for the recognition. So they're even, right? This is divisible by 2 and this is divisible by 2. The root 5 might as well just be an x or something, right? Like 6x over 14. We're not doing anything with the root 5. So 3 root 5 over 7. Oh my god. Under an hour.